Good morning. We'll do a presentation about solving large-scale problem using JuMP. My name is Thuener Silva. I'm from LUMP's laboratory. And this presentation is a little bit different from the other ones. Michael said yesterday something about the back-end part, the front-end part. We have the back-end when you're talking all about these solvers. And in the front-end, we're talking about these frameworks. In this presentation, I will focus more on the user part, how you use the JuMP to solve those kind of problems. And my agenda for the presentation is just talk a little bit of our laboratory, some research projects, some commercial research projects that we had. I do a lot of benchmarks. You see many benchmarks from different languages. I want to show this from the community. I will talk a little bit about SDDP use. The SDDP has some different ways to use JuMP and to use solvers. I want to talk about a little bit of this. And I will finish up with some thoughts of how we are using JuMP and Julia on our laboratory. So LUMPS is a laboratory at PUC Rio. We have now more than 20 students between PhD and master students and research also. We have many professors there that the laboratory. They come from different backgrounds, optimization, statistics, and temporal series. Most of the problems that we had is on energy, but we also have some problems in finance and oil and gas production. Why we started using JuMP? I had some previous work in Julia, but we had to have a big and a good framework, optimization framework in the language in order to us guys to have to use. Because we are optimization guys, so we cannot go to a language that doesn't have this kind of framework or doesn't have other optimization guys that use it. So JuMP was the major reason that we changed to Julia. It's a very good language, don't get me wrong on that. There is nice performance, but if you don't have JuMP, we couldn't migrate to Julia. JuMP is very versatile and easy to use, even for an undergrad. If you have a background on optimization, this is very easy to use. We have some issues with using optimization and some other language, for example, MATLAB. It's very bad on optimization. So if you have a commercial product that uses MATLAB, many times you have to use another language, like Moselle, to optimize the model. And this it was very bad for the final product. And we also got stuck with some kind of solver. If you use, for example, in your case, Express, everyone uses Express in the laboratory. You cannot change that solver because you're so accustomed using it, and you know all the details, how to use it. If you have to change to Cplex or Gurobi, it would be a huge change. You cannot do that easily. So that was a big thing for us. We can change the solver easily, and we can test different solvers and see which solver you should use for each problem. Okay. So just some of the projects. Those are commercial projects. We know that Julia and JuMP has a very good, successful history with academic research, but we also have some very successful projects using Julia and JuMP. Some big projects. The common thing about all those projects is that all they are using Julia and JuMP, and all this problem has a huge database. So for example, in the first one, you have churn and fraud detection for credit card companies. There's a huge database. Imagine the number of transactions that these companies have on one day, for example. The second one is an energy problem. You have a high-frequency series on that problem. It's some challenge to work with that. Some database can even work with this large number of that data. The third one here is the Android framework, and we also dealing with huge data from Brazilian hydro and thermoelectric generation. The last one, it's optimization for oil and gas production with uncertainty. There's also a challenge there. There are a lot of binary variables. Some of the models have something more than 1 billion binary variables. It's difficult to solve it. I'm not getting in details of this model. If you want to know more about it, you can ask me later. Okay, so just a little bit on my history with Julia and JuMP. It was about 2014. We discovered Julia and JuMP. About that time, we are trying to use it in many cases as we can. But I was finished my PhD, and my advisor insists me to port everything to Julia. But I was 2 years developing C++, so I didn't do that. I didn't have the courage to do that. So as soon as I finish my PhD, I start my postdoc at PUC Rio, and now I have time to port everything from C++ to Julia and JuMP. So the first thing that I do in many languages that I try to benchmark it with the other ones, and this was the first benchmark that I did. I think this is Julia 0.5, and you can see here the pre-compilation time. If you have something that's small, some small instance, you have a huge difference between the Julia and C++, but it's a smaller time. But if you scale up, you can get a very close time between Julia and C++. And one special thing about this is that I developed this C++ for something like 2 years, and the Julia code was done in less than a month. Okay. So I was convinced about the huge success in academic part of the Julia and JuMP use it. So now I'm trying to convince everyone else on the lumps and also the teacher to use it, to use more frequently also. I had a research problem that it's a humanitarian logistic problem with endogenous uncertainty. You have a master problem with MIP and also some non-linear constraints. It's a little bit like similar to Bender, the composition. We had cuts to add. I had previous research did this code on Moselle using Express. I do 2 versions of this code. First one in C++, the second one in Julia, using Cplex. It's a little bit difficult to compare those methods when you have different gaps, optimal gaps. But if you are satisfied with 1% gap, you can see that Julia has a huge advantage on this case. I'm not sure why there is this huge difference between C++ and Julia, but maybe it's because I'm using Concert on C++, and in Julia we are using the C library. We know that Concert is a little bit slower than the other. But this is initial code. I didn't turn in those code, not the C++, neither the Julia code. Okay, just the initial code with no enhancing performance. The other thing that I talk about is the advance of JuMP in Julia. You can change the solver whatever you want. So for this problem, I use 3 different solvers just to see which is the best for my problem. I test Cplex, Grob, and Express. And for this case, Cplex was the best one with much lower times than the other ones. Okay. Another problem that I have, it's a hydro dispatch problem with integers variable. We use some mixed inter round cuts on this problem. That's not a very good implementation of that, just again, some initial implementation. We did some cutting plane, branching bound, and branching cut algorithm with that. The first implementation was done in MATLAB, and the second one in Julia. The big difference here, if you're using some small instance, no problem, the time is closer. But you can see if you have a more big instance, MATLAB can be 10 times as lower than Julia code. Okay? Initial code for both of this. Another application that I had is a machine learning code. We use support vector machine. If you don't know anything about it, no problem. But imagine a matrix with the columns are the dimension of the problem, the features of the problem, the lines are the points of the problem. And we are increasing those dimension and points to see how JuMP and Julia will behave using Cplex and also in C++. So you can see that for the small problem, no problem at all. If have more bigger problem, you have some difference there, but not that big one. Okay. So now I will talk more about SDDP. I don't know if you're familiar with SDDP, but I don't have time to get in detail about the methodology. I just want to show how SDDP is different from that other one applications that was being successfully used in JuMP. So the SDDP is a methodology to solve multi-stage stochastic problem. I think it was, in many cases, the best one to use. SDDP, there is a trick in SDDP that you can see on this Bellman equation, that SDDP approximates the future cost function, this guy here, with a piecewise linear approximation. So we'll do a forward step and a backward step, adding cuts to this problem. And the special thing about SDDP, the stochastic dynamic dual program, is he used the dual variable to construct those cuts. Okay, but the important thing here to see is that SDDP is a different application because you are interacting a lot with JuMP and with the solver. You are adding a lot of cuts in different problems. You have a lot of problems, sub-problems. So you're always adding constraints to the model and always changing the right-hand side of the model. So just to know how to use SDDP, when you converge SDDP, what you end up with, it's a future cost function at each stage that you can use to question about the decision. So for example, if you have a portfolio allocation model and you have the allocation that you want to go with it, you can ask for this function, what will be the future return if I do this allocation? Okay, so at each stage you have some future cost function that you can use on the optimization. So the SDDP was a special case, and in the beginning I was having some issues using JuMP. The first model that I developed in C++ would get about 100 gigabytes of RAM. If I port direct to Julia, I will double that value, so I couldn't use it in a machine with that amount of gigabytes. So it was a computation bottleneck to use directly JuMP. And also, if I couldn't remove the constraint, I couldn't lower this use of memory and optimize the memory consumption. There was also later a performance decrease compared with low-level API. I will talk about this more later. Okay. So how did I solve those problems? I was very happy with JuMP. I was using many problems. So I would try as much as possible to use JuMP in all the applications. So I did all the construction of the model. That's much more easy to read when you change the model when you're doing JuMP. And as soon as finish the construction of the model, I start to use low-level API. So all the constraints and all the right-hand side are doing on low-level API. The downside of this is that I have to choose a solver. So I did a benchmark using all JuMP and change the solver. And this is the best solver for me. It's Simplex on this case. Okay, I don't have the older version of this code, but I have a new version of this code that uses much less memory than the other one. The memory on this case here was not a problem, but the surprise here is this time consumption when you use JuMP instead of using low-level API. So just to detail more what's happening here, when you are adding constraints on the backward step of the SDDP, the code was 2 times slower than the low-level API. And when you're evaluating the bounds, just changing the right-hand side of the models, we are 3 times slower than the low-level API. So I opened an issue in 2017 about this. We're talking a little bit more. And my question with that was there is a limit to what we can do with JuMP. For example, I know that other people developing SDDP in JuMP have to do also this, have to use low-level API. But my hope was that in the new version, this should be much better than that. So I did a benchmark on that day. using some different ways to add constraints, just to know if there is a better way to add those constraints, and comparing everything with Cplex API. So it's just a model here, a simple model. It's very easy to solve. N is the dimension of the problem, and I have a lot of cuts here. I have many cuts, and I will benchmark all this implementation of adding constraints to the model. So I add 300,000 constraints to the model. My dimension was 100. The model, just to know, the model is solving in 5 seconds. It's an easy model, just a toy problem. And I do 2 runs, because sometimes when you benchmark Julia, the first run you precompile, and the second one sometimes is much faster than the first one, but I didn't see this on those cases. So we have the vector one, the scalar one, the second scalar, and also the Cplex API. You can see that there is a huge difference if you're using vector one. It's better to use scalar constraints, to add constraints using scalar way. But also I did some comparison between the different version of Julia and JuMP versions. So the first one is 0.6, and I'm going to 0.7, and later 1.0. And the last 2 comparisons is between the JuMP 0.18 and JuMP 0.19. Okay. So you can see that there isn't much increase on the time when we are changing Julia, but there was an increase on the time when you're using JuMP 0.19. Again, don't be mad about these results. I just want to show and to know how to solve this problem, and what is happening here with the new version of JuMP. I had the results. The important thing for me on this part is that I did this benchmark to show that improving on JuMP, that we had improvement in 0.19, and I was sad about these results. I also checked the memory consumption. There isn't much decrease in memory consumption during those versions. But yesterday during the
Are you just saying maybe you should try to use direct mode if you want to learn?
Yes, exactly. I was saying. So yesterday during the Benoit presentation, now is the good part. I thought that the right way for this problem, if you have direct mode for this problem, and I was talking with Oscar yesterday, and he said, "Oh man, use the direct mode; it would be much better." So that's calm down. Okay.
The improvement you're doing that is something that we just simulation is reallocating the space to your constraint. So in the example that you showed, you create a constraint inside of the macro, but if you reallocate them outside and then just fill up a dense array, it speeds up a lot. But it's okay. Even the problem is only your all these constraints are
it's just going to you don't have to store these constraints. Okay, so I tried yesterday to use direct model. I just refreshed the benchmark. This is a different machine, so I'm showing the new benchmark with another machine. And the direct model was very, very good. I have some real improvement on the memory consumption. We have half of the memory consumption from the other way to use JuMP. This is a very good result because we are seeing just many different ways that you can use JuMP, that many different layers that you can use it. Okay. Okay, I will talk about that. I know that this is a very huge improvement from the direct model, the model that doesn't use direct model. But it's a little bit worse than the other version. But I think if we can improve this time here, if we can fix some of the regression, this will be much closer from the low-level API. I'm very hopeful with that. I think this will be much better version of JuMP, and I thank you, JuMP-dev guys, Benoit. And the other ones that developed Joaquin, Miles, and Oscar for that. And just to wrap up, what's happened since we started using JuMP, we're much more happy. We changed the way that we are developed software on LAMPs. Now our projects are on Julia, and now the courses are using Julia. And we are trying to give more back to community. We are trying to create more frameworks to give some feedback to community. Also, we are having some very successful projects with a small team of persons. You don't have to have a very good developer to do this product. And since then, we have more than 15 publications using JuMP and Julia, and at least 14 in development. Okay, thank you.
Any questions from the audience?
If you have any doubts about the benchmarks, or if you want to know about those, you can ask me anytime.
Have you posted those?
What?
Have you posted the
Yes. It's I did some change yesterday, but I will refresh the code.
So the same issue?
I will put in the later.
Excuse me, we're going to set up the.
It looked like one of the changes there was like the Celix version up on.
So let me log in
So
here.
this is for Celix.
Yes,
Do we have some?
increase in time.
Yeah, some understanding what's going on there.
Yes, I don't know what happened there, but was
Te voy a sacar.
30% of increase. Oscar said